Kotlin Conf. Super excited to be back doing conferences and back here in Amsterdam again. My name is Ryan Harter. I'm an Android engineer at Dropbox. Today I wanted to share with you some exploration and experimentation that I've done with using Kotlin Native for CLIs. In order to do that, I'm going to be using an open source project of mine at Dropbox called Differ. So to give you just an idea of what Differ is it's a Kotlin Multiplatform image diffing library. So this is very similar to diff that you might use at the command line. We use it with Git all the time, all that kind of stuff, but for images. And this is, Differ is the image comparator. That was a weird way to say that. The image comparator behind DropShots, which is another open source library for on-device Android screenshot testing. So to lay some groundwork, a little about Differ and what it looks like. It's a really simple library. The basis for it is this interface, is the image comparator. And you can compare two images, left and right. You can optionally provide a mask, get some more information. And then it returns a comparison result, which has some information about what's different about these images. At its core, Differ doesn't know anything about thresholds or pass, fail, any of that kind of stuff. It just tells you what's different about images. And then we've got some images there. So this is what that looks like. This is a Kotlin Multiplatform library. So in the common source set, we have a very simple interface. An image is something that has a width and a height and something you can get pixels out of. And for this purpose, a pixel is just a color. What is the value at that position within the image? So that's the interface in the common source set. On the JVM, it looks like this. We wrap a buffered image, which it comes from AWT. And on Android, we use a bitmap. Very simple. That's kind of the basics of it. And this isn't a sales pitch for Differ, so I'm not going to go into too much more there exactly. But for how it's used, DropShots, I mentioned, an Android screenshot testing library. So imagine you make an app that displays images of adorable kittens. Which is a bit of a betrayal because I'm a certified dog person, but still adorable. You're running your app. This is what it's supposed to look like. You want to make sure there aren't regressions. So you write a test. You store this as the reference image that you want to compare against. And then using DropShots, which uses Differ under the hood, using that mask that I talked about before to figure out which pixels are different, by how much, what kind of thresholds do we have, whatever. You can catch regressions, visual regressions. And so, you run the test for a while, and then you end up with this. You get that cute little guy peeking up there. And, you run your test. It highlights the differences, all pretty straightforward. So that's Differ in how it's used. And as I mentioned, Differ is a Kotlin Multiplatform library, which looks like that. And DropShots depends on it, but for any open source project, you need a sample project, right? Something that people can see how to interact with this library. And so for that, we have the Differ CLI. That's the sample project that's included. And image diffing is something you can do in CI. It doesn't have to happen on device or anything like that. So a CLI is a great example of how to exercise this. It also, incidentally, makes the development workflow real fast because you're just building on the machine. You don't have to install on device or any of that kind of stuff. So CLI here. What's a CLI? CLI stands for Command Line Interface, which means that Differ CLI is just a terminal program that you can use just like any other that you use on Mac OS, Linux. I hear Windows these days. And so what does that interface look like? We think about interfaces as like, our UI is a graphical thing that we interact with. But, all of these programs we use at the command line also have an interface. And so In this case, this might be an example. It's only partially made up, but you call an executable. You have different flags and options that can either be present or not. Some might have values, some might not. Different complexity there. And then in this case, we pass 2 cat pictures. And then when we run this, this is what we get. We told it to be verbose, so it spits out a bunch of information. And then to be a good citizen at the command line, this actually sets the result code to 1 for failures and 0 for passes. That way you can use it in scripting and all of that. So this is the interface we want, right? When we're using other tools at the command line, this is what they look like. And we want to make a program. I guess we don't generally call them applications when they're at the command line, but we want to make a program that looks and feels like any other we might use. But when I made the CLI for differ, the first one that I made for, I don't know, probably out of habit, I just made a JVM app like any other. I used the Kotlin JVM plugin. And so instead of this, what I really get is something more akin to this, right? This is the command line. You have to have, you have to run Java. You have to give it a class path, which I put in question marks so it would fit on this slide. And then, once you get the class path with all the jars there, then you need to specify the class that contains the public static void main function that you're going to run, and then you can pass arguments to it. And that's, if I went back to my team at Dropbox and said, hey, we got this great tool, go use this, nobody would ever touch it. And, CI is a great use case for, command line tools for this. And of course, with this, we then have to, we first have to install Java. We probably wouldn't do that with Homebrew if we're in CI, but and then that class path we were talking before, what is that? That's really just a pile of jars, right? And so, we have to distribute this pile of jars. We have to extract them somewhere. And, what's the standard place to put your pile of jars? I don't know, your download directory? Who knows? You have to know where they are so that you can run it. So all of this, sort of first got me thinking, this is, kind of a pain for this multi-platform library, CLI front end. On top of that, as a good, I've been developing for Android for 12 years or something, and as a good Java developer, I've gotten really good at accepting everybody else saying, you know how slow Java is, and the JVM's so slow, and all that kind of stuff. So, the voice inside my head was saying, we have this, it took 338 milliseconds. Is that good? Is it bad? I don't know, but, everybody's been telling me for the last decade how slow Java is, so, I bet a native application could do better than that, right? So that got me thinking about, this is a multi-platform library, so why is this CLI that I created, written for the JVM? Why not use Kotlin Native for CLIs? Most is not backed up by any data at all. A lot of command line programs that we use every day are, C programs, they're native programs. Why not do that? We have Kotlin Native at our disposal. And, a few questions I had was can we make it feel native? Can we avoid dealing with class paths or wrapper scripts and piles of jars and all that kind of stuff by moving to Kotlin Native? What about dependencies? How is that handled? Do we make it just one binary that contains all the dependencies, sort of like a fat jar, or can we deal with other stuff? When I want to install a new command line program, all I do is, brew install or DNF install or, whatever that might be. Can we do that with Kotlin Native? What would that look like? And can we make distribution easier? I don't want to have to distribute a zip file of jars that you're going to have to remember where they are or something so that you can do this. And finally, again, that I'm a bad Java programmer. Can we get better performance from native development, right? Using native tools. So to answer these questions and sort of explore this, I migrated Differ's CLI to Kotlin Native. this part's going to be real quick. There's any tutorial on the web will show you how to do this. This is a reasonably simplified version of like what the build script used to look like. Update the JVM plugin to the multi-platform plugin. Move your dependencies around so they're in the common source set, and then add some targets. I left the JVM target on here because I wanted to be able to do some comparisons. I added, Mac OS x64, Mac OS ARM64, Linux x64. You can also do Windows, I guess, but then with Kotlin Native, you have to tell it what you want to make, right? You can make libraries. You can make shared object libraries, .sos, like the native. The native equivalent of jars, right? In our case, we want to make an executable. We want to make some binaries. So, we do that, and you'll notice that like you specify the entry point. That's really similar to the Java application plugin. You have to specify the main class and all that. That's about it for the mechanics. So let's get into those questions. The first one I had was like dependencies. What does that look like? Managing dependencies in a native world. And so, we have the differ CLI. That's our like the application effectively that we're making at this point. That obviously has to depend on differ, otherwise it's all kind of moot and pointless. We also depend on Kotlin X CLI. That is a tool. Command line arguments can seem fairly simple and straightforward, but they're fairly complex when you consider they need to be read in any order. Some of them have parameters, some don't. They should be typed and all this kind of stuff. Kotlin X CLI is a great library for Kotlin Multiplatform library to parse all of that natively for you. And my first run through of this talk was like an hour and a half, so the 30 slides about Kotlin X CLI are not in here anymore, but I recommend checking it out if you're interested. And then lastly, we need something to load images. We need an image loading library. We're doing a native thing, so these other two are Kotlin Multiplatform libraries, but our image loading library, we're going to go native, so we need to figure something out there. And so we need to take a moment to talk a bit about the choices for dependencies when you're working in native environments. And so there's really two options here. You can either have statically linked dependencies or you can have dynamically linked dependencies. And the idea is either way you go, we have this like dependency tree that's about the same. This is what we saw in the last slide. And at the end of the day, we want to create an executable. That's the output of our build, right? And so with a static dependency, or with static dependencies, that's similar to like the shadow plugin or like fat jars, where all of those dependencies just get shoved right into the executable. And there's some benefits to that, which I'll talk about a bit later. But on the dynamic side, it's a bit different. The Kotlin multi-platform dependencies still get shoved into the executable because Kotlin C is going to compile them, into the resulting executable. However, the native dependencies that are dynamically linked are going to be provided by the operating system. All right, and this is another important point that we'll get to later. Now the question is like why would you choose one or the other? And so like in this example, this is a pretty simple app. We don't have a lot of dependencies and that kind of stuff. So it's not terribly apparent, but as our dependencies grow, statically linked dependencies, they're all getting shoved right into the executable, which means your executable grows, all right? Same thing if you're shading jars, making fat jars, which is the same idea, unzip the jars and just pack them all into the same, to the same jar. The dynamic dependencies, on the other hand, the executable hasn't changed at all. And, again, reasonably trivial because you still need those dependencies on your system. However, as you get more packages and libraries and tools on your system, it starts to look like this, where these statically linked dependencies, these may all be the same dependencies, but they're repeated, in all of the executables across the system, which means they're taking up disk space, the executable's larger, it takes longer to download, all of that. Whereas on the dynamic side, those are shared dependencies. incidentally, I think like this is similar to what for the Android developers in the room. This is similar to what Google Play does with Android X dependencies, where Google Play doesn't need to ship like I don't know the view model package or Android X activity with every application. It can be shared on the system. For this experiment, the static dependency that I'm going to be using is STB image. The dynamic one is libPNG, and these are both image libraries. We'll start out with STB image. STB image comes from the STB library, repository, which you can find at the link on the bottom of the screen. And it sells itself as single file public domain libraries for C and C++. This is something, I picked this because I've used it a lot in different, I have a history in graphics, so different like graphic tools that need to load images and stuff. This is a great tool for that. Something like for separate from, we live in a JVM world where we have access to, Maven and Gradle and dependency managers and central repositories and like all that kind of stuff. C and C++ kind of has a history that it doesn't have, I mean, it has some solutions to that, but no, like, it doesn't have like Maven, everybody, anything's available somewhere via Maven. And so the idea, especially for, not necessarily for, your production builds and that kind of stuff, but if you're working on internal tooling or you're working on weekend hack project or like any of that kind of stuff, the idea of having a single file library in that kind of like C, C++ world is really nice. It makes sort of like managing dependencies for especially a lot of that kind of thing a lot easier. So anyway, so what does this look like? I went to that GitHub repo down there, and that's not my repo. So I downloaded the stbimage.h file, put it in the C interop folder, and then created this definition file. And if we open up that def file and look at that, this is part of Kotlin Native C interop tool, part of the build pipeline. And what we have here is headers. You list which headers from the library you want to include. Header filter, which in this case is the same, but the idea is there are certain libraries where like maybe you don't want everything that's in some huge megalib. You can filter so you're only taking portions. And then we have the package. C, C++, well, C++ does, but it's like C doesn't really have namespacing, but in Java we use packages for namespaces in the JVM world, rather. And so this just lets the C interop tool know when it creates the bindings for the public API that's in this header file, what package is it going to be under. And then you get this little separator here, and after that separator is just C code, all right? So that's basically, you could add stuff for your own header. So the idea here is that if you have a library that maybe the API isn't quite, it could use a couple tweaks on the native side to really interoperate with Kotlin really well or something like that. This is where you can do that in a reasonably easy way. In this case, STB image, you just have to define a macro so that it knows to actually, implement the stuff one time so it's accessible. Not important. If we go into the header file, like a lot of these single header libraries, it's very, very well documented. And we get down here into basic usage, and you'll see it's real simple. We have an STBI load function. We pass it a file name. And we need to pass in some int pointers, and this is how it's going to return data about the image that it's loaded. And then it returns unsigned char pointer of the pixel data. This is an array of unsigned chars. And then you'll notice down at the bottom there that we're not in a memory managed environment. So when we're done with this, we're going to have to free that. So what does this look like in Kotlin when we're trying to map things together here? This is implementing the image interface. We need a width and a height, and here we need we're gonna store a pointer. This is going to be for that data, the pixel data, and the type here you can see is C pointer of type ubyte var, which is fortunately not opaque at all. But that's roughly the equivalent to the unsigned char pointer, because chars are just bytes. And then when we want to load this, we want to actually implement it, we can just call that STBI load function. Because of the C interop tool that comes with Kotlin Native, it's available, as an import. We can do that. We get some data back. It's not quite exactly how we want it because of some, void pointer magic. We have to reinterpret it. Reinterpret is just a type of cast in the native world, so not super important. The STBI load function returns null if the image is malformed or it can't load it for some reason, so we deal with that here. And then you'll notice, I did some hand wavy stuff. Remember, we had those int pointers we needed to pass in, and that's kind of a question. Like in Kotlin, right? We don't have pointers, right? You just trust the JVM to manage, move around, do what it wants to with the memory that's holding what we need, including deduping, inlining, like all sorts of optimization. So what do we do here? This kind of gets into the like some of the complexity with interoping with native libraries. What we need to do here is we need to create an arena. And an arena, I don't know, out of the C++ world, it's basically a way that you can allocate a bunch of memory in an arena, in like a space that you can then easily just deallocate it all later. Right? All this stuff we never had to think about in our memory managed environment, but we create an arena, we try finally blah, 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 so that it always gets cleared. And then using that arena, we can allocate memory. And the important thing here is that, like, the JVM, when our code is running in the JVM, I mentioned before, like, you don't have any rights to memory and pointers and that kind of stuff. The JVM can reorganize. It can, during garbage collection passes, it might compact things, and there's a lot of stuff that it does with memory. So the location in memory where it's storing your variables and that kind of stuff is not stable. So we have to work around that when we're interoping with APIs that expect it to be. So we allocate some memory within this arena for 3 ints. These ints have technically they have values of probably whatever happened to be in that space of RAM. But the important thing here is that we can get pointers to them. So now we have a stable chunk of memory that we can pass to the STBI load function so that it can fill that memory with information. And then once that function's returned, it has filled that memory with information. Now we can get the values out of it. And then that's kind of the end of that loading. We'll hit the finally, the arena will be clear, that space in memory will be returned to the system to do what it wants with it, and that's it. And then just to wrap things up, we had that you have to be able to get a pixel. This is not super relevant, but just some information about how to get the offset within the array of pixels to a pixel. And then that pointer that we had before, a nice thing about it is that we just get array access to that. So effectively, we're able to get the RGBA channels out of that stream of data at the correct offset for a pixel to get the colors of it. And then we can return it. And finally, we can't forget that we have to close this. We have to return that that chunk of memory that we reserved before. And so, not quite as simple as what we saw before, but overall not too bad. That's what it looks like to interop with this particular native library. libPNG, I'm not gonna go into all the details. libPNG, if you don't know what it is, it's the official PNG reference implementation, and this is, if you run Linux, it's installed on all the systems and all that kind of stuff. libPNG's, it's been around for like 100,000 years or something. Everybody knows it, right? So in this case, since we're going to dynamically link this, the benefit is that, a lot of things use libPNG, especially if you're in, like the Linux world or that kind of stuff. So we're not going to statically link this. We're going to rely on the operating system to provide it to us. So we don't need a header in here. All we need is that libPNG definition file. We open that up, and what do we get? Pretty similar. The top part, I won't bore you going over that again, but we've got some new stuff in here. Since this is dynamically linked, i.e. provided by the OS, we have to tell the compiler a couple bits of information. We have to tell it where to find the headers. And the headers, if you haven't done a lot of native development, in C and C++ and probably other languages I haven't used, you have like a header and an implementation file usually, and the header is effectively like the public API or the public interface for whatever you're implementing. And so when you're writing and compiling the code, you need to compile it against that header. And so in this case, we need to tell the compiler where to access those headers. And that is system dependent. So on Linux systems, it might be in one of those two locations, user include, and in OS 10, depending on if you use Homebrew, depending on if you're on an Intel or Silicon Mac, it might be in opt Homebrew or it might be in user local. But that's the basic idea. It'll just search in that file, those directories for the header file. And then this, we move on to linker options. And so, when you compile, you need the header because that tells the compiler, like what functions do I expect to have access to and where do I find them? Well, when you're executing the code, you need to be able to actually have the implementation. So a lot of times for static libraries, this might be a .a file. For dynamically linked files, this might be a .so file for shared object. But again, there's standard places on different systems of where that's located. You have to tell the linker where to get that. So it's first going to compile the program, then it'll link it to tell it where to go, and that's it. This is the libPNG implementation, not going line by line, because as I mentioned before, it's been around for like 100,000 years. It does almost everything, and it's a lot. But, that's fine. It works. So that's the implementation there. So those are for managing dependencies, those are sort of, two approaches in the native world. So let's take a minute to compare that to the JVM, right? For this particular case, for image loading, I'm going to use image.io. Image.io is part of the JVM. It's the, you'll find it's stuff in the javax.image package, and this is, JVM, not Android. That's it. So, I showed this before. It's pretty simple, but I should point out I did cheat a little here because, in the other implementations, I passed in a file path and we had to do all the loading there, and here I just kind of pass in the buffered image and you take care of that on your own. So, so this isn't entirely accurate, but it's also with purpose. You'll notice this class is private because using a standard Kotlin convention, I'm exposing a public function that, is image, because the fact that, on the JVM, we happen to be using buffered image to implement this is an implementation detail. And so this is a standard Kotlin convention to allow you to expose constructor-like functions that hide the implementation detail. But what you'll notice, I was being a little disingenuous by doing the loading elsewhere, but also kind of not, because that's the part where you go from a file path to a buffered image. In this, I do want to be clear and point out that this is not like, JVM figured everything out and native is so hard. This is like, these are idioms for the platform, and someday there might be a wrapper for libPNG that puts a nice UI on it that sort of hides all of that for you. But at this point in the Kotlin Native community, we're not there yet. We don't have access to all of the stuff that we have in the JVM world. So that's it. And if you remember, I kind of went into this thinking well, maybe dependencies would be a little easier, and we could access some native stuff there. But in this case, the JVM kind of, really just won out. So moving on, next up, the next question was about performance. I've heard forever that Java's so slow, blah, blah, blah. It's really tiring. So, what does native look like? In this case, we're going to go back to STB image and libPNG. And as I run this to test this out, I added some more logging and that kind of stuff. And you'll notice this is with STB image. And we've got the load times here. of like 95, 96 milliseconds, which is like, these aren't big images. This was actually tested with the Adorable Kitten photos. They're not like terribly big images, but you know, I don't know, is that a good load time, bad time? I don't know. But you know, I noticed the comparison time was like a second and a half on this. And this is the, I spent a lot of time, instead of working on slides, you know, playing around with this because it's more fun. And so this is like the sort of the heavily optimized, like doing a lot of testing and that kind of stuff. That's about as low as I was able to get it, right? Also caveat that with, you know, I am a professional, but you know, I'm not an expert at that. But there are a lot of different options with like how memory is handled. You know, I was exploring like, is the fact that we're sort of crossing the bridge, you know, using a native pointer directly that we have to access for every pixel, is that, you know, better or worse than copying all of the pixels into JVM managed memory and all that kind of stuff? And this was the sample I showed before, the implementation, that was the most performant that I could get, and it was, you know, accessing native pixels. But that was about what I could get. So this is actually where I started. You know, I used STB image a lot, and I in the past, and so I started there, and it was a bit demoralizing. And so I thought, like, well, STB image is not optimized for performance; it's optimized for portability. And so that's when I actually decided to go try out libPNG. Oh yeah, there's the times. And you know, here's what I saw with libPNG. Like the load time for PMGs was, you know, it cut it in half. It was great. But also, you know, like less than 100 milliseconds to less than 100 milliseconds, like wasn't, you know, that's not the bottleneck here. Notice the comparison is still, you know, 1600 milliseconds. And so, you know, between these two, you know, I managed to, boy, shave off some load time, but shave off like 7 milliseconds of comparison time. So that wasn't really great. And so let's compare that to you know, Java and the JVM now. And if you've had to deal with hearing about, you know, how slow the JVM is, you know, it's important to understand that like that was true a long time ago. There's been a lot of optimization since then. So this is the example now. You know, the load times are, you know, a bit, I don't want to say all over the place, but they're, you know, they're pretty mixed. What I think is happening, and this is where we get into like Ryan guesses about things. So, you know, just to be clear, you know, what I imagine is happening here is there are some resources that need to be loaded the first time that you're going to load an image. You know, statics, you know, static utilities, things like that. And then the second time, we're able to do things really fast. There's also a lot of optimizations about, you know, how the JVM manages stuff. Ooh, time. But here's the real important thing, is that the comparison time here was like order of magnitude different. And, you know, again, I had explored before, you know, maybe on the native side, if I copy all that pixel data into, you know, into like JVM managed memory, it would speed up comparisons, and it did. But it also increased the load time for every image because now we have to copy all this data over. So, you know, it's kind of a trade-off. So, you know, here we got like, you know, we got this, and it was startling how, you know, how I guess wrong I was about this assumption that like we're always going to be faster here. And so again, like, you know, the JVM kind of won out. And I do want to, you know, point out, this was, you know, this case, you know, there are a lot of cases, I'm sure, that, you know, where you can do different optimizations and different stuff. But, you know, in my testing in this case, this is what I got. Your mileage may vary, blah, 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 tell my lawyers. Last question was distribution. So how do we distribute this? When I started this, I was thinking about like, oh, you know, I'll use STB image, I'll, you know, build a, you know, statically link it, you know, like on the right, and then we just got like an executable I can hand out to people, and boom, you know, there we go. So you know, I'm thinking like, oh yeah, you use curl or wget or whatever you want. You just download the binary, and that finishes up. What happens when you try to run it? It runs. You know, it's great. That's perfect. That's exactly what we want, right? But that's also not the whole story, because you don't really have this what you have is something like this, where you don't download the differ executable. You download the differ executable for macOS ARM64 if you're on ARM64, or maybe you download the differ executable for macOS x64, or for Linux x64, or any number of other things. So what that really did was, there's still a burden of that, but it moves it from the consumer to the developer, to whoever's managing this, this open source project. They have to maintain a build pipeline that's going to build for any platform anyone could want, or somebody's going to have to build it themselves. Looking at the dynamic example, it's, do the same thing. You download the executable, you try to run it, and womp womp, you get this, right? Error while loading shared libraries, no such file or directory. And what happened here? Well, we mentioned before that with dynamically linked executables, the OS is going to provide the shared library, and we don't have the shared library on this OS. So then you use whatever tool you use for your system to install libPNG. It does some things and works real hard, and then eventually you get to run it again and everything works. So that's like, a different problem. That's another problem because, this is also a native binary, so we still have the per platform thing. But now we also have to, manage dependencies. Now, if you were managing a real project that you wanted people to download and use that, didn't work somewhere near you, or you could go help them do it, you wouldn't do that, right? You wouldn't say oh, here's the executable, but go download all these dependencies, right? You would make a homebrew package, or you would make a DNF or an apt package, or for whatever platforms you want to do. But that's also more, you have to understand the dependency management systems for all of these platforms, and you have to manage multiple releases to different systems and all that kind of stuff. So adds a lot of complexity. So what does the JVM look like here? This is a little interesting because in the native things, what we're building, our output is an executable. But that's not the case with the JVM. With the JVM is the executable. And what we're building is the dependencies for it. And this is evidenced by the fact that what you run at the command line is Java, right? That's the executable. It's not anything that you've done. You give it the class path. I actually put the class path in here. This is all of the jars, that this depends on. And then you give it the main, the class that contains the, static void. I don't know, I don't write all that anymore. I just let IntelliJ do it, so I can't remember it. But then you can finally, include your arguments. But this isn't what we wanted, right? This is something a little closer to this. This is if you use Shadow plugin or fat jars. The idea is you can make an executable jar, which means there's a resource somewhere in there that specifies that main class for you, so you don't have to. You're still running Java, and you give it a jar, and then you can put the stuff after it. So it's still not quite as clean as we had hoped. And this is where we get to the 7 minutes left. This is where we get to the kind of, if I'm being honest, the embarrassing part of the talk. I submitted this. I was, having fun doing all this, and then for whatever reason, I randomly ran GradleW tasks, and I noticed this interesting section about distribution tasks, and I was, I don't know why I'd always passed over it before, so I took a look and. A couple things that kind of looked interesting there, and in particular that install dist. So I ran it. Hey, what happens? And this is what I see in the build directory, right? There's that install directory has a bin and a lib directory, which is kind of reminiscent to POSIX file systems, right? Where you have user lib, user bin, all that kind of stuff. And there's all my jars in the lib directory, and then there's these two things, these two little guys in the bin directory. And that, of course, that looks a lot like that GradleW script, right? The wrapper that we use. When we want to run Gradle from the command line, Gradle's in Java. Well, Gradle's in a lot of things, but it's written for the JVM, right? But we don't ever deal with class paths and all that kind of stuff. We do. We have the GradleW script that looks something like this. Opening those up, that's exactly what it was, and. this was far enough into the slide, the prep, that I was like, great, Gradle introduced something new to the application plugin. That's cool. I went on GitHub and I looked at the history, and it's been there since at least 2015, which is what makes it really embarrassing. But for some reason, I never paid attention to that part. But what these scripts do is, you can install this. You can use that tar dist or that zip dist. You can install these in the normal POSIX locations, and now on your path you have, in this case it's named CLI because that's the module name, but you have a CLI binary. It's a script, but nobody ever needs to know that. If you install it on the path, you don't have to, give the path to it. It just shows up like any other command. And this is how it works, right? So the whole goal here was to, and then you run it and it does all the things you'd expect it to. So the whole goal here, right, was to get, get this like CLI tool to really like feel and, like a native, any other native tool at the CLI. Turns out almost forever we've had that available for Java applications. And so in the last few minutes, just to finish up and kind of recap, I kind of went into this thinking that like native dependencies might be a little easier to manage or something like that, and that definitely ended up turning out like not to be the case. It can be okay, but that also means you make a trade-off there where you end up having to deal with a lot of things like memory management, like non-idiomatic APIs and that kind of stuff. So that was a little disappointing, and performance, right? JVM's so slow, you got to go to native if you want to do anything with real performance was also not the case. The last 15 years, there have been a ton of optimization in the JVM, and it's really come a long way. So that's great to see. Distribution, I went into this thinking, I'll just make an executable, and especially if it's statically linked, just give it to people and they can run it anywhere. As long as, I recognize what platform they're on, and I've built it for that platform, and any of my colleagues with an Intel Mac, get the different one, and yeah, that ended up not being quite easier. What I really learned about this is that it's really important to, test your assumptions, just like this. This was a great exercise in that, to see what works for you. And so these same assumptions and learnings that I took away, if you have different needs or requirements or different things you're integrating with, they might not, end up the same way as they did for me. So that was the real winning takeaway here. And also I got to use the cool sparkly animation that I never use because it's over the top. But anyway, that's so that's the end. I really appreciate everybody coming out. If you want slides, they're available there. You can find me on Mastodon. I'm Ryan, and I'm happy to chat afterwards if anybody wants. Thanks, everyone.